Welcome to our revision session on wave motion. So today we are going to be learning about transverse and longitudinal waves with their examples.
And we're also going to be learning about electromagnetic waves, velocity in a vacuum, waves transferring their energy, and the wavelengths and frequencies of different electromagnetic waves. So, common properties of electromagnetic waves. They are all transverse. So all electromagnetic waves are described as transverse waves, and they can all travel through a vacuum. Now, they all travel through a vacuum at exactly the same speed, and that's the speed of light, which is 300 million meters per second. All electromagnetic waves transfer energy. And they can all be reflected, and they can all be refracted. However, they're not all the same, and they differ in two ways, and that's the wavelength and the frequency. So next we're going to go through the properties of a wave. So here we have the peak of the wave, and this is the highest point, and it is above the rest position. So the rest position is the undisturbed position of the particles or fields when they are not vibrating. Down here we've got the trough, and that's the lowest point of the wave. Here we have the wavelength, which is the distance covered by a full cycle of the wave, and it's usually measured by either the peak to the peak or the trough to the trough. This section here, this is known as the amplitude, and that's the maximum displacement of a point of the wave from its rest position. So obviously earlier we said how all electromagnetic waves are different. There's many different types, and they differ in two main ways, and that's the frequency and the wavelength. So here we have waves that have got a long wavelength and they have a low frequency. So they have a large distance and the amount of the cycles is low. And over here we have short wavelengths, high frequencies, and a high amount of energy. So at this end would be waves like radio waves. Next, once the wavelengths are slightly shorter and they have a slightly higher frequency than the radio waves, you have got microwaves. Moving on from there, you would have your infrared. Moving on from there would be a section that you're most common with, and that's visible light. So that's the light that allows for our vision. Next, when it's getting even shorter and even higher frequencies, you have ultraviolet light. After that would be your X-rays. And then the electromagnetic waves, which have the shortest wavelength and the highest frequency, all the ones down here are your gamma rays. So we've just talked about the different types of electromagnetic waves. So I want you to give me some examples of what might we use radio waves for. So the next question is, what might we use microwaves for? Now, I'm not on about the ones in your kitchen, although have a little research and see if they do use microwaves in their microwaves. So next, I want you to go through this table, write it down on a piece of paper or on your computer, and I want you to go through and fill it out for the different wave types that we've just spoken about. I want you to give me their wavelength in meters And I want you to give me a couple of different examples of where they might be used. So I'll go through and I'll do radio waves for you as an example so you can see what I want from you. And then you go through and fill out the rest. So we know that radio waves have got the lowest energy and the lowest frequency. And from research, I found that a typical wavelength in meters is just 1. And then a couple of uses is stuff like radio and TV. Now, it's really important that you remember the order of the electromagnetic spectrum. So we're going to come up with a little mnemonic, and you can come up with your own if you don't like this one, for going down and decreasing wavelength. So for our R, we're going to have rats. For our M, we're going to say rats and mice. For our I, we're going to say in. For our V, we're going to say Venice. For our U, we're going to say use. For our X, we're going to say extra. For our G, we're going to say gondolas.
Hello and welcome to this video looking at how waves transfer energy. You should be familiar with several different types of waves, such as water waves, sound waves, the whole range of the electromagnetic spectrum, and you've probably looked at different types of seismic waves caused by earthquakes as well. All these different waves have some properties in common. They all transfer energy from one place to another, and none of them transfer matter. As the wave moves through the material, the particles vibrate. They might vibrate perpendicular to the motion, they might vibrate parallel to the motion. But as the particles vibrate, they transfer energy and information to the particles next to them. These in turn pass them to the particles next to them. In this way, energy and information is transferred by the wave. But at each time, the particle ends up back where it started from. So the particles don't move. The material that the wave's passing through doesn't move from where the wave started to where the wave ends up. The material stays where it is. So that's why we say waves transfer energy, but not matter. Okay, it should be expected to describe evidence for waves transferring energy and not matter. You'd be expected to be able to do this for sound waves. So the example we're going to look at here is in a guitar string. As the guitar string is plucked, the string will vibrate back and forwards. It will transfer energy and information to the surrounding air particles, but the string will end up back where it started from. It isn't transferred. As the surrounding air particles have energy transferred to them, it will cause them to vibrate up and down. This vibrational energy will be passed on to the surrounding air particles, causing those to vibrate and pass energy on to the next air particles. So in this way, the energy is moved away from the guitar string outwards, eventually to our ear, so we hear the music. But what doesn't happen is the air particles moving away. After the vibrating, they go back to their starting position, the same as the string has done, same with the air particles, they go back to their starting position. If they did move, what we'd get is a vacuum. All those air particles would move away and we get left with a vacuum in there, which we don't. So this is evidence for sound waves transferring energy and information, but not matter. We also need to look at water waves as examples of waves transferring energy and not matter. So here we have a pool of still calm water, and we're going to drop a twig into the pool, and we would see ripples, waves move out from that source to the edges of the pool. This is our energy moving away from the source. But if this was a still calm pool of water, the twig wouldn't move. It would bob up and down, but it wouldn't move outwards to the edges. This is evidence that waves do not transfer matter, because if they did, if the water particles moved away from the source, we'd see the twig moving with the water particles. But we don't see the twig moving, and this is because the waves do not transfer matter, they only transfer energy and information. So now it's time to check our understanding. We're going to look at these two questions here. First one, what do all waves transfer? Energy, money, matter, or particles? And the second question, Keith is trying to prove to his brother that waves do not transfer matter. He uses water waves as an example. Discuss the evidence he may have used and explain why this proves waves do not transfer matter. So pause the video now, have a go at these questions, and then I'll check back with you in a minute. Well, what do all waves transfer energy? Well, let's work down the list here at some of these. It's clearly not money. That's just a silly answer there. It's not matter. We've just said waves do not transfer matter. If it doesn't transfer matter, it means it doesn't transfer particles. Remember, the particles just vibrate side to side, but they end up back where they started from, which leaves us with energy, which you knew was the right answer all along, didn't you? So waves transfer energy. And the second one here, trying to prove to his brother that waves do not transfer matter. We're going to discuss the evidence that we may have used to explain why this proves waves do not transfer matter. Or if you remember, we talk about dropping the twig into the pond. The ripples will move out from the twig, but the twig doesn't move away with them. This shows that whilst the waves move out from the twig, transferring energy, they do not take the twig with them, which means they do not transfer matter. And just remember, waves transfer energy, but not matter. Okay, and here's your exam review. See if you can do these ones on your own. Which of the following do waves never transfer? Is it information, matter, energy, or none of the above? And the second question, with reference to matter, energy, and particles, explain how waves travel through a medium. Make sure you use those keywords there. Good luck, guys.
So question 1, which of these is not a property of an electromagnetic wave? They can travel through a vacuum, they are longitudinal, or they transfer energy from one place to another. And yep, the answer is they are longitudinal. So question 2 is what is different for each type of wave in the electromagnetic spectrum? Is it the speed, the frequency, or its ability to travel through a vacuum? And obviously the answer is frequency. So question 3 is which of these types of waves has the highest frequency? Is it radio waves, ultraviolet, or visible light? Make sure to use that mnemonic to help you remember. And now hopefully you'll have used that mnemonic to find out that it's ultraviolet light.
So now we're going to talk a bit more about the waves themselves. So waves are one way in which energy may be transferred between stores. So energy is Now the thing you need to take notice of is the fact that energy is transferred. Now, both mechanical and electromagnetic waves will transfer energy without matter being transferred. So there's another point to make. Matter is not transferred. And finally, waves transfer energy as radiation from the source of the waves to an absorber. So they transfer energy from a source to an absorber. So question number 1, what do waves transfer? Is it energy and not matter? B, energy and matter? Or C, matter and not energy? The answer is in fact A, energy and not matter. So question number 2, what is the name of the arrow here? Now it is described as peak to peak. So is it A, the wavelength, B, the amplitude, or C, the frequency? And the answer is in fact A, the wavelength. So from peak to peak or trough to trough, that is what is known as the wavelength. So now we are actually going to diverge into 2 different types of waves. The first one is longitudinal waves, and the second type of wave is transverse. So longitudinal waves are waves where the oscillations are along the same direction as the direction of travel and energy transfer. It's also important to note that longitudinal waves show areas of compression and rarefaction. Now I'm going to show you what that means. So longitudinal waves have areas of compression where the waves are compressed, and areas of rarefaction where the waves are slightly spread. So I'm now going to give you 3 examples of longitudinal waves. So the first one, sound waves. Sound waves are in fact longitudinal, and additionally ultrasound waves and seismic P waves are both longitudinal. So the second type of wave is transverse wave. Now, unlike longitudinal wave, where the oscillations move in the same direction, oscillations in fact move at right angles to the direction of travel and the energy transfer. And like we covered before in electromagnetic waves, they are in fact transverse also. And it's important to note that all electromagnetic waves travel at the same speed for a vacuum, such as space. So some examples of transverse waves are ripples on the surface of water. Another example is a Mexican wave. That is in fact an example of a transverse wave. There's seismic S waves. And another example is the vibrations on a guitar string. And you will notice the shape of a transverse wave. Unlike longitudinal, where it was compressions and rarefactions, a transverse wave is in fact shaped like this. So I am going to show you a video now, and I would like you to pay attention as I will be asking questions following the video.
Waves transfer energy from one place to another. You should already know how to describe them in terms of frequency, wavelength and amplitude, which we looked at in another video. In this video, we're going to look at 2 ways they can be classified. Waves are produced as a result of vibrations and can be classified as transverse or longitudinal. Whether they are transverse or longitudinal depends upon how the particles are made to vibrate as the energy passes. Let's look at longitudinal first. This is where the particles vibrate parallel to the direction in which the wave of energy is travelling. Notice that the ends of the slinky don't ever leave the hands holding them. It's only the energy that travels. The places where the coils or particles are bunched together are called compressions. Where they are furthest apart are called rarefactions. An example of longitudinal waves is sound. When a drum is struck, the drum skin vibrates, which causes the air particles next to it to vibrate. This causes the next air particle to vibrate, then the next, and so on until the vibration reaches the ear, causing the eardrum to vibrate. The vibrating air speeds away from the source, creating a sound wave. Let's look at another type of wave, transverse waves. The hand moves up and down, as does the slinky, but the wave itself moves from left to right, so the particles vibrate at 90 degrees to the direction that the energy is moving. We can simply think of it as, in longitudinal waves, the hand pulses horizontally, pushing and pulling, and the wave energy also moves horizontally, back and forward. Whereas in transverse waves, the hand moves up and down, but the wave energy still moves horizontally. Again, the ends of the slinky never leave the hands holding it, it's just the energy that moves along. Transverse waves are usually used to show the wavelength and amplitude. Pause the video and see if you can remember how to label the amplitude and wavelength on the diagram. Did you get them right? The waves on the surface of water are transverse waves. They make the water surface go up and down. All types of electromagnetic waves, like visible light, are also transverse waves. So, now you should be able to describe the differences between transverse waves and longitudinal waves. Remember, it is the energy and not the slinky itself that travels.
So now you've watched that video, I'm going to jump straight into question 1. So which of the following statements is false? Is it A, in transverse waves, the vibrations are at right angles to the direction of wave travel? Is it B, compressions are areas of low pressure due to particles being far apart? Or is it C, electromagnetic waves are transverse waves? So the answer is in fact B. Compressions are areas of high pressure due to the particles being close together. Now, if it was low pressure and the particles were far apart, they would be rarefactions. So question number 2. Which of the following is an example of a longitudinal wave? Is it A, vibrations on a guitar string? B, sound waves? C, a Mexican wave? Or D, ripples on the surface of water? And the correct answer is in fact B, sound waves. Sound waves are in fact longitudinal, whereas the rest are transverse.
Thank you for watching our revision tool.
We hope you've learned everything you need to know about wave motion.